Next, the components of the refrigeration cycle will be the variables, okay, will be estimated, will be calculated, okay? And I'll minimize here. And this is the problem, okay? Simple refrigerator cycle, okay? Here I have the compressor, okay? Look, attention here, okay? The fluid, okay, is ammonia. It receives energy from this equipment, from the compressor. So the compressor, okay, the fluid gains energy from the compressor, okay? So this is a fluid, okay, is a liquid, okay? And there's a valve, okay, the expansion valve, okay? In general, the design of expansion valve is based on Joule-Thompson, okay, process, okay, which the enthalpy at 3, okay, is the same as enthalpy at 4. And also this process is adiabatic, okay, it doesn't lose any heat to the environment. So that's expansion valve. The purpose of the expansion valve is the temperature, okay? This is 3, you have the upstream temperature. At 4, you have downstream temperature. This is the flow, okay? This is the flow, okay? And so the enthalpy, upstream and downstream, they are the same, okay? By hypothesis, by assumption, okay? To derive the expansion valve process. Now this is the evaporator. What's the purpose of the evaporator? Okay, the environment, okay, loses heat, okay, to the fluid inside the evaporator. That's why it evaporates, okay, because it receives heat, okay, from the surroundings, from the environment. And then compressor, okay, transform, okay, gas into liquid, okay? Now, you can see here on the right, this diagram, there's a temperature, okay, Kelvin or degrees centigrade, okay? And this is the entropy, see? This you can see the states. Obviously, you don't see 2 prime, because 2 prime doesn't exist here, because 2 prime is the saturated, okay, vapor, okay? This line here is only vapor, okay? And this line here is only liquid. 2 is a superheated vapor, okay? It's high, very high temperature, okay? Now, 3 and 2 prime, okay, they are saturated, okay? They are in the states here, okay? The states between 3 and 2 prime, they constitute of vapor and liquid. Likewise, from 4 prime to 1, okay? So this is a saturated region, because if you know the temperature, okay, at this line over here, 4 prime to 1, the pressure is the same, okay? You find out the pressure, okay? That the temperature and pressure, they are the same. Now, you can see down here, okay? Look, from 4 prime to 1, the pressure is the same. You see here? This is the diagram, this is the pressure and enthalpy. You see that's important because the process from 3 to 4, okay, look at the left, 3 to 4 is the expansion valve. The enthalpy remains the same, okay? And this 1 to 2, okay, is the energy gained by the fluid, okay, from this equipment over here, the compressor, okay, which increases the temperature and increase the pressure, okay. This is from 1 to 2. That's the real, okay. That's actual energy, okay. 2 prime is the state, okay, which it has the highest temperature here, which is 40 degrees, okay, and this TL is the low temperature, this is -5 degrees centigrade, okay. I'll show it down here, okay. Now this is the equipment, okay, the refrigeration cycle, and then we'll talk now here about the table. Okay, this is the ammonia. Okay, this is a table. This is minus 5 degrees centigrade. Okay, and this is 4 degrees centigrade. This is saturated. Okay, all of this. Okay, now F here is a fluid. Okay, HF at minus 5 degrees centigrade is H4 prime. Okay, the unit is kilojoules by kilogram. The value of the entropy at state 4 prime, okay, is 176.9, okay, kilojoules by kilogram. Likewise, on the other side, when there is only gas, okay, the H sub G is equal H1, kilojoule by kilo is 1456.1. Okay, that's the entropy. Okay, all these are on the table. Okay, I can find out in the table. Okay, likewise for 40 degrees, I have the same procedure. Okay, to get those numbers. Okay, there is no develop here to obtain this value. Okay, now. This is a parameter, it's a capacity, okay, of the cycle, okay. TR, okay, is ton of refrigeration, okay. This is a number, it is given 25. This is a unit, 1 ton refrigerator is in general 210 kilojoules by minute, okay. This is the power, attention now, kilojoules is energy, divided by time, okay, is power. Okay? Now, it's divided by 60, I transform minutes in seconds, and this is 3.5 kilowatt, because kilojoules by second is kilowatt, because by definition, 1 watt, okay, let's write here, by definition, 1 watt corresponds, okay, to 1 joule by second. Okay, that's the definition of watt. Now I'll raise here. Okay, let's continue. Okay, so this is a very important parameter because this is related, okay, to the mass flow rate of the refrigerant. Okay, now this m dot r is refrigerant. Okay, this is symbol here I will use throughout this. R is refrigerant here. I'll put it over here. Okay. Now the flow rate, okay, is the capacity divided by this is called cooling effect. That's interesting. You see, H1 minus H4. You see, look at that. That's the energy used. Okay. You see, the energy used, okay, is from H1 and H4, minus H4. This is from the evaporator over here, okay? Because why? Because the environment has some heat, okay, in which I would like to transfer to the fluid. Okay? That's why the fluid evaporates, okay, because it gains heat from the environment. Okay? That's the purpose of the refrigerator cycle. Now, let's start over here. So, this is what we call R sub capital E. Okay, this H1 minus H4. Okay, is the used heat. Okay, H1 minus H4 is the used heat. Okay, now. This I have here from the table, okay, but which is important is this, okay, I'll show you there, okay, look, this is important. You see, H3 is equal H4 from the expansion valve, okay, the enthalpy is the same, so I substitute H4 by H3, which I get from the table, okay, because this is a liquid, okay, saturated liquid, okay. On this side here is saturated gas, okay, at the temperature of 40 degrees centigrade temperature, okay. Now then, as I said, I substitute H4 by H3, which I can obtain from the table. So if I divide 87.5, which is Q dot R, divided by the cooling effect, okay, which these numbers I get from the table, then I obtain the mass flow rate, okay, 0.08. Then I put unit, that's for you to see, okay. So the numerator, Q dot R, okay, is kilojoules by second, and the denominator, okay, is the kilojoule by kilogram with the enthalpy, okay. I cancel kilojoules and I get kilogram by second, okay, with the mass flow rate. So this mass flow rate I will use throughout this solve the problem over here. Okay? It will be the same, okay, because by assumption, I'm assuming a steady state, okay. So the mass flow rate will be the same throughout the cycle, okay. Now what I want first to calculate the entropy at the exit of the expansion valve, okay. The exit expansion valve is the state 4, okay. I just showed them the figure again, okay. Look, here, it's here, okay. This is the exit of the expansion valve. Now, what I want also is entropy generation. Attention now, the compressor, okay. This is lambda dot C here as the compressor, okay. Now I ask, second law of thermodynamics is violated, okay. I'll find out there. Now, the third item, the entropy generation. I know that the entropy generation of the expansion valve, okay. This is lambda dot V, V is the valve, okay. And finally, the coefficients of performance. And also, I would like to find out the power, okay, due to the compressor, okay. This is a COP, means coefficient of performance. Now, I'll make some assumptions. It's very important to solve the problem. Now, first one, each component is analyzed as a steady process, okay? There is no time variation, okay? So partial derivative with respect to time of any state variable will be identically 0, okay? Now, the second assumption is the compressor operates adiabatically. So there is no heat flow, okay, out from the machine, from the compressor, okay? Q dot from 1 to 2. Attention now, compressor, okay, is the state, look, for 1 to 2, okay? There's a diabatic process, but it's not isentropic. Attention now, okay? It is assume a diabatic. Okay, some exercise, okay, they assume also isentropic, okay? This will be helpful. Well, it will be easier to find out some parameter there, okay? But this, I'm assuming, okay, that this is not isentropic, okay, the compressor, okay? Likewise, in the valve, okay, the expansion valve, I'm assuming also adiabatic, okay? Now, the second law is violated, I'm just asking, because in this case, I'm calculating, okay, the entropy generation, okay, using obviously the second law of thermodynamics. Now, here, okay. Now, I'm here the assumption, okay, the expansion valve, okay. You see, Q dot 3 to 4, okay, is the 3 is the upstream of the valve, the expansion valve, and 4 is downstream. I'm assuming this process is adiabatic, but it's not isoenthalpic, okay? It's not. it is, okay? The entropy 3 at 3 is the same as 4, okay, by assumption. Now, another sum, the variation of kinetic energy and potential energy are neglected. The variation are neglected, okay? There's no variation in any component, okay, of potential energy and the kinetic energy. But the enthalpy, okay, I cannot neglect it because they change a lot, okay? Now the solution, okay, the first solution you see here, okay, I can add entropy at the exit of the expansion valve, okay? Now, you see at 4, you see that. That is, I want, okay, the entropy at 4, okay? Do you remember where is 4? Okay, just the downstream of the valve, okay, it's right here, okay? I want the entropy right here, right at this point here, okay, S4, okay? Now, let's do this. Okay, before doing this, I will define, you see, look at here, look. The state 4, it contains liquid, okay, and vapor, okay? Because it is in this region between 4' and 1. 4' only liquid, okay? 1 is only gas, vapor, okay? But 4, okay, it has the state, okay? At 4, it has vapor plus the liquid. That's why we define in thermodynamics what we call the quality, okay? Definition of quality, X4, okay? Because the temperature is 40 degrees, I'm at state 4, is H4 minus H4 prime, okay? Look, I just wrote here just to make you look at here, quite easy, okay? This is 4 prime, okay? This here is only liquid, okay? That's only liquid. This is only gas, okay? So you define the quality, this difference here, H4 prime, okay, divide by the whole length over here, okay? That's what we call quality. Just look at here, okay? You see that you have H4 minus H4 prime, okay, in this case, okay, and you have H1 minus H4 prime, okay? Just I put the color just for you to see it, okay? The same, okay? This is the green one, okay? I just put the green one here, okay? And this is the denominator, okay? That's a numerator. That's to see the color, you see easy how to get it, okay? Now, what is good because, okay, H4, I have H4. Why I have, look at that, it's easy, look. Why I have H4, okay? And I don't have S4, entropy H4, but I have H4 because from the assumption, okay, because of the expansion valve, okay, H4 is equal H3. H3, okay, it is sitting, okay, on the liquid line, okay, and that's from the table, okay. Just look at the table, but the table at 40 degrees. Attention now, okay. H4 it is at 0 degrees, but they are the same, okay. So I go there and bring, okay, from the table H3, which is equal H4. Look, it's right here, okay. And this number here now on the table, this H1 in the table, because H1.1 is on the vapor line, okay? Only the vapor line, okay? And H4 prime also in the liquid, okay? So I have this number over here, okay? H4 I don't have, but state 4 is downstream, okay, of the valve. Okay, the flow of the valve, okay, which is equal to upstream. See this upstream, okay, this here is downstream. So they are the same, okay, because expansion valve. This helps us to find out the quality, okay. So this is a number quality. I will use this quality, okay, look at that, okay, just to find out now the entropy at point 4, okay. Attention now here, okay, at point 4, don't forget, you have liquid plus vapor, okay, vapor. Don't forget that, okay. At 4 prime, I have only liquid, okay. At 1, state 1, I have only vapor. But at 4, okay, is between 4 prime and 1. That's why I have liquid plus vapor, okay. Now I write it over here. Let's continue, okay. That's the first item. This is just numbers, okay. You have to get your calculator and do this, okay, quite easy. So then I found out, okay, I calculated S4, okay. Look at the unit, kilojoules by kilokelvin, okay. It's energy by mass by temperature in Kelvin, okay. This is S4. Now I have H4, I have S4, okay. Now compressor, okay, the second item. Okay, I'll calculate entropy generation, okay, of the compressor. Attention now, please, attention now, okay, by assumption, okay, by assumption, the process of any component in a steady state. So the derivative with respect to time, okay, is 0, because nothing varies, okay, with time. The volume. Here the surface, okay, controlled surface, okay. Now, as I said in the last videos, okay, you can see there, this is a sign, have a sign, okay, this is a dot product, okay. Now, here the fluid, okay, the upstream, okay, the fluid is getting to the compressor, okay, this state 1, and is out of the compressor to this state 2. Okay. So the sign of this dot product here at 1 is minus, okay, minus m dot r s1. At the exit is plus m dot r s2. And remember that from conservation law, conservation of mass, okay, conservation of mass, okay. Conservation law of mass, okay, m dot 1 is equal m dot 2, okay. Then what I did previously, okay, some exercise, okay. Now this is why I have this. I put, okay. Now remember from the second law of thermodynamics, the right hand side, okay, which is related to derivative with respect to time, to the system. Now the system here is the compressor. Now the system is the compressor, okay. Now I have compressor and I have the environment, okay. But by assumption, okay, the process in the compressor is adiabatic, so the fluid doesn't lose, okay, heat to the surroundings, okay. So this is by assumption, okay, by assumption, okay, it's adiabatic. So the left hand side will be the generation of entropy in the compressor, okay. I just move this to the right hand side, the left hand side, okay, and the left hand side I move to the right hand side. Now S2, attention now, okay. Look, I will show you there, the picture of it there. I'll show you here, it's easier, look. I have here 1, remember, I have here 2, okay? This is 1, 2. Now T2 is given. Okay? T2 is known. It's given. Okay? by assumption. Okay? T2 is known. Okay? Now T1 is given because T1. Do you remember? Look, I have a curve over here. Remember? Okay. This is only vapor. Only vapor in this line here. Do you remember one here? Okay, comes from the evaporator here. This is one. Only vapor. This is from the table. Okay? And also, do you remember the saturated temperature, okay, at T1 is equal minus 5 degrees centigrade, okay? Because it's in the evaporator. The evaporator is for 4 to 1, okay? At temperature at 1, I know, okay? Now, what I will do it, now it's quite easy because you can see here, I'll show it down here. See? You see? Now I don't have S2. Okay, I don't have because this is superheated vapor. Okay, you remember? This is superheated vapor. This is vapor. Okay, the temperature is high is given. Okay, is 70 degrees. The temperature at 2. Okay, is given 7 degrees centigrade. I think so. It is. Yes. Now I will find out S2. I don't have S2, okay? But we can find S2. Now it's quite interesting here. This is 1, okay. And I'll show in the figure, so it will be better for you. Okay, look at that. It's quite easy. Go there. Look at here. You see? S2 prime. Okay? The temperature here, I know, is 40 degrees. Okay? Now, what's important, and this line, you see the red line here? Okay? This is the pressure, is isobaric. Okay? All here. You see, all the states here remain the same pressure, okay? The same pressure. So I can derive, okay? If you remember, let's put down there. Compressor, okay, I'm here, okay? If you remember, it's quite easy because from the first law you have TdS is equal dH, in this case, minus V dP. Okay? Now, it's important here because if the isobaric means dP is equal 0, so dH is Cp dt. Now ds is equal, you see, I divide by Cp dt over T. So if I integrate here the S from initial state to final, for instance, okay, in general, okay, then, let's see here, put there, just no, don't hurry, okay, to final, this is not fluid, okay, this is final, okay, this is Cp is constant, which I give, the integration of dt of T, this T initial, T final. Look at here, this is a logarithm, okay? This is equal Cp natural log of Tf of the I, okay? Now let's go back. Let's go back in here. That's why it shows the logarithm. You see, look at the logarithm here. It's quite easy, okay? So S2 is equal S2 prime plus Cp log, okay? This is the final temperature, is the superheated, okay? Divided by temperature at 2 prime, okay? You see, quite easy because it's isobaric, okay? The line which I drew there is isobaric. Now I can calculate now S2. Okay, why do I need S2? Just to calculate what I want is the generation entropy in the compressor. Okay, here I have S2, which I'm getting right here. It's quite easy. Okay, now this is from the table. Okay, S2 prime is from the table. Why? Because 2 prime belongs to the line which there is only vapor. Okay, at temperature of 40 degrees, I got from the table. Cp I know is given. Temperature T2 is known. So this will be 70 plus 273. Okay. T prime 2 I know because it's a 40 degrees centigrade plus 273. Attention now, okay? Don't put degrees Kelvin here, please. It's only Kelvin, okay? There's a mistake that some books write. Centigrade, you put the centigrade, degree. Kelvin is not degree, okay? You just add of this. You find out the logarithm, okay? This is 343 divided by 313 in this case. This is find out this number from the calculator, you get 0.2. My goodness. So the temperature at 2, okay, the superheated vapor, you just add S2 prime to 0.2. You see this 15 plus 0.2 is equal, okay, this is I think, I'm sorry, this is 0.02. Then you show this 0.02 here. We just go to the calculator and see, okay? Okay, no problem. 0.02. Okay, then it'll be now this will be 5 point. You keep 0.02, be 7 here, 0.7 here. Now I know already the difference, okay? Okay, because the difference is right over here, okay? Is S2, okay, minus this number over here, okay? Just what I got over there, okay? Now, so now I can multiply times 0.08, okay, times 0.02, okay? This will be just from your calculator, just quite easy. You find out 0.016, okay? You multiply. Kilojoules, okay? You see, this is kilogram by second, okay? This m point r, okay? M point r is kilogram by second times kilojoule, kilogram, and Kelvin, okay? Because it's now it's quite clear. I cancel kilogram, it's kilojoule by second with a kilowatt. Okay. Now it's important now because obviously S2 is greater than S1. Okay. So the entropy generation is positive. Okay, which means that it does not, the process in the compressor does not violate, okay, the second law of thermodynamics. That's quite clear. Okay. Now let's go to the expansion valve. Okay, the entropy generation. Okay, let's put it here. Here I drew the valve, the expansion valve. This is upstream. Okay, at state 3. Don't forget, this is at 40 degrees centigrade, and this is downstream, is minus 5 degrees centigrade. Okay. Now the enthalpy is the same. Okay. Now attention now, please, attention now. I'm going to use again. Okay. Let's see. I already wrote there. I'll use again that formulation what I did for the compressor. Okay. Now the assumption is a steady. Okay. And this look at here. Look. Here I have inflow, okay? At 3 I have inflow, at 4 I have outflow. In flow, the dot product is negative, okay? The same what I said before, okay? The outflow, the dot product is positive, okay? Now, by assumption, also is adiabatic, okay? In the expansion valve, okay? According to the Joule-Thompson, okay, hypothesis. So I got only the right-hand side, okay? The generation of entropy, V as a valve, okay? Now I put here, okay, this one on the right-hand side and this one on the left-hand side, okay? And S4 minus S3, attention now, S4 I already obtained. Do you remember? It's there, okay? I can get from there. I already did that. Okay, S4 I calculated S4. Look at here. Look S4. Okay, now state 4, okay, is a mixed between vapor and liquid. Okay, now I got it S4. I calculated. Okay, it's better colocar previous calculation. Let's see. That's it. Previous calculation. Okay, and S3. Okay, 3. Don't forget that. Okay, 3 is a point at 40 degrees. Okay, look at here. Look at here. Look. And the 3 belongs to the liquid, okay, saturated liquid, okay, from the table, okay. Then I write down over here 1.6437, 1.712, okay. I multiply by the mass flow rate, okay. Look, I put the unit just for you to see the answer, okay. This is the generation of entropy in the valve is 0.0055, okay. Kilojoule by second divided by Kelvin. Attention now. Look, the unit, okay, this is related to the entropy, okay. The entropy is energy by, in this case, okay, energy by Kelvin, okay. When I divide by second, I put a dot over here, okay. Now, this is 0.05. Oh, there is a note. I'm sorry, a copy in here. There is double O here. This is 0.00555. Okay, then I multiply over here, and then I have this is the answer. Okay, point. Okay, double O here, 55 kilowatt by Kelvin. Okay, attention now, kilowatt by Kelvin. Okay, kilowatt is kilojoule divided by second. See, this is kilowatt. Okay, and this divided by Kelvin over here. Now let's go to the last item. Okay, the last item is the COP. Okay, look at that COP. What means COP? Okay, if you look, I just drew over here. Okay, look, just for you to understand, just to avoid to go down there. Okay, I just put this evaporate. Do you remember? Okay, 4-to-1 is evaporate. You see the heat. This heat comes from the surroundings. Okay, to evaporate the fluid. Okay, obviously. Okay, 1-to-2 is the compressor. Okay, what it does? The compressor. Okay, transform. Okay, vapor to liquid. Okay, that's the idea of the compressor. Okay, that's a 1 and 2. Instead of going there, okay, before to show the figure, just show here. Okay, just for you to understand. Look, okay, we pay. Okay, when we use a compressor, we pay. Okay, for that. Okay, now what I paid. Okay, the energy I paid is H2 minus H1. Okay, you see the entropy. Okay, now what do I get when I paid from 1 to 2? I get just, okay, to transform the environment, okay, to lower the temperature of the environment, okay, in which obviously the fluid, okay, the refrigerant, we get the heat. That's why it evaporates, okay. Now, this is the evaporate used. This is a used energy, okay. H1 minus H4 is the energy which I used, okay, to refrigerate the environment, okay. And 1 to 2 is what I paid for the compressor, okay. I need the compressor, okay, to send energy to the fluid. Why? Because I want to transform, okay, gas into liquid, okay. I do this using a compressor, okay. Now, what the coefficients of performance, okay? Look, H2 divided by H2 minus H1 is in the denominator, okay? This is what I paid for, okay? Now, H1 minus H4 is what I use, but, okay, H4 is the downstream of the expansion valve, which is equal to H3, okay? This is, look, H4, okay, I just cross here, okay, and put H3. This is from the table, okay, H1 is from the table, okay. Now, I need to calculate H2. I don't have H2. Do you remember the temperature here, okay? This is a super heated, okay? Do you remember that? S2, I calculate S2, but I don't have the entropy over here. And I need the entropy to calculate the coefficient of performance, okay? No problem. I'll get H2 the same way, the same procedure as I did for S2. So this H2 prime, okay, which is from the table. This is the capacity calorie, the specific calorie, okay? This is the difference in temperature, okay? Now, because this is T2, which is given, I didn't calculate it. This is given, okay? And T2 prime is quite easy because T2 prime is the temperature at 2 prime, which is 40 degrees, okay? So if I subtract, okay, T2 minus T2 prime, it will be 30 degrees. Why? Because you have 70 minus 40. Professor, I want to transfer this to Kelvin. Doesn't matter because you add 273 here and subtract 273 over there. So that you can, when you have a subtraction, okay, you just use the degrees centigrade, no problem, it will be 30 over here, okay? Because T2, okay, is given 70, and T2 prime, okay, is 40, okay? In this case, it's 40 degrees, okay, the hot temperature, okay? Now, this I have 30 over here. I have this number CP is given, okay? And H2 prime is from the table. So I get this number H2 here, okay? No problem, okay? And I multiply this number so I can calculate H2, and I just put that right over here. Look, I calculate H2, you see, from here, okay, this number. I just plug in here, okay? Then I do this calculation, okay? And then the coefficient of performance is just 1065.5 divided, this is approximately 100, okay? That's why I put 100 here. You divide by 100 is 10.66. It's dimensionless, okay? This is dimensionless because the unit in the numerator is the same unit of the denominator. So the coefficient of performance is dimensionless. But what I did here, just I didn't ask, but I did later, after I did that, I'll calculate the work, okay? I calculate the work. So I just put in the other side because I finished here. Now, calculate the work of the compressor, okay? I use the first law of thermodynamics, okay? Attention now, here. You have to pay attention. What is the first law? Look, the first law for the closed system. Closed system. Okay, is this. Look, now, this is a differential of the energy, okay? Now, if I increase, if the fluid, okay, or receive heat, okay, it increases the energy. But, look, this is very important, first, if the fluid receive, look, put in the place of the fluid, okay, you are the fluid, okay? If you receive energy, okay, if you receive work, the energy will be increased. So that's why when you have pump, okay, the power of the pump, it just will be negative. First you have to say, okay, I want a pump of 2 HP, okay, horsepower. But you don't ask this when you buy a pump, you don't put the minus 2 HP. You just, I want a pump, okay, with the power 2 HP. But this minus here is important. Why? Because the power of the pump, so suppose you have here Q minus, here is the pump, okay? Let's put dot here, okay? This is a derivative, this is the total energy. Let's talk this, okay? Now, the pump, what the pump does, okay? The pump, okay, the fluid receives energy from the pump, from the compressor, okay? But it loses energy to the turbine, okay? Because it's just the opposite. So when you get the power of the pump, power compressor, this to plug in the first law, because there is a minus over here, this has to be minus minus. So this will be Q dot minus 2 HP, for instance, okay? Because the energy, the variation energy, okay, has to increase, okay? Let's put here, has to be greater than 0, okay? That's why when you calculate the power of the pump or power of the compressor, okay, the calculation you find minus. But please, if you go to the market, okay, and choose a pump, a power of a pump, never say, oh, I want minus 2 HP, okay, of power. But on the first law, because you put here a minus sign, okay, the sign of the power, okay, is negative for the compressor. Likewise, okay, in the opposite argument, okay, the power of a turbine, okay, will be plus, because a turbine, this minus here will have to remain, because in the turbine, the fluid loses energy to the fluid, okay? So, this is a closed system, okay? For the open system, instead of U, you have plus kinetic energy plus potential energy, okay? That's the difference between closed and open system. Already discussed over this, okay? So the first law of thermodynamics, okay, the power that I'll calculate has to be negative, because I have, for the compressor, I have this minus power of the compressor, okay? The energy have to increase, so this d of dt, t, and this has to increase, okay? Has to increase. So this has to be minus, because minus is plus. Okay, let's do this, okay? Now this that equation, okay, which relates system and control volume, okay? This is steady. I'm applying this to the compressor, okay? But to this is the first law of thermodynamics, okay? What I did before, okay, to calculate the entropy generation was the second law of thermodynamics, okay? This is the first law, okay, the energy. Now this is the power of the compressor, okay? Now this, you see, the variation of kinetic energy and potential energy, the variation, I'm not saying the kinetic energy is zero, okay? I'm saying the variation is zero, okay? Now, then I'll apply, you have inflow, okay? You see, do you remember that? I have one here, okay? And two here. Here I have inflow, here I have outflow, okay? This in, this out. Why this is important? Because the dot product, okay? So in the inflow I have negative, okay? That's why, look how it eats now, okay? This minus here is because I have inflow at 1. This plus here is because I have outflow, okay? Now there's a flow rate, okay? This m dot r, I just rearrange this term over here, okay? This h2 minus h1. I remain minus here, see what I mean? Now, this is 0.08, okay? This is the flow rate, mass flow rate. And this difference here is around 100, okay? As I did before. This is 0.08 times 108 kilojoules divided by second, 8 kilowatt. This minus here is important, okay, because the compressor, the fluid gains, it receives the energy from the equipment, okay? Now that's a work done on the fluid, okay? The fluid receives work from the compressor, from the pump, okay? That's it.